So Mohan is going to talk about, well, you can read the title.
Yeah, I'm not even going to give them time to read the title. I'm moving.
Okay, go.
Okay.
Go ahead.
So if any of you have seen my, say, workshop talk, this is my attempt to try and do it better, because this is a subset of what you've seen before, I guess. Okay, so let's get started. What am I going to talk about today? So I'm going to talk about discovering axioms and stuff, but first the overall big picture first. The big picture is that we started out saying we want to develop an architecture that has the following things. First, it should be able to use, or that is represent and reason with different descriptions. And for the purposes of this talk, I'm going to make it the qualitative and quantitative descriptions of incomplete domain knowledge and uncertainty. And by qualitative, I'm here going to restrict myself to talk about common sense knowledge and default statements of the form, the cereal box is usually in the kitchen. And by quantitative, I'm going to talk about probabilistic representations of the form, I'm 90% sure the cereal box is in the kitchen. But in addition to that, because I'm dealing with incomplete domain knowledge, I'm also going to add on this thing of saying I want to interactively acquire domain knowledge and be able to either augment or revise the existing knowledge. And when I talk about knowledge here, I'm primarily talking about the preconditions and effects of actions and action capabilities, such as a robot with a weak arm cannot lift a heavy box. How do I figure things like this? And all the way through, though I won't talk about this here, it's there in the papers, is we want to be able to establish that the robot's behavior satisfies certain desirable properties. Okay, so that's good. Let's try a block diagram description of what the architecture is about. So imagine, if you will, that there exists within this robot a logician and a statistician. The logician has a course level description of the world and is going to use non-monotonic logical inference with the knowledge that is there to do planning, diagnostics, and a whole lot of things. And for any given goal, the logician is going to come out with a plan of abstract actions. Now each action corresponds to a transition in his transition diagram. So that transition is sort of sent off to the statistician, who is going to work with a fine resolution description of the world and is going to do probabilistic planning, like visual perception, scene understanding, and stuff like that. And whenever the statistician has something to report, the observed outcomes go back to the logician. So that is a closing the loop. Right? Okay, so, and this, if you notice, includes reasoning with incomplete knowledge, planning, learning, all those nice things that we like about. Right? So what is different, or what is interesting here? Okay, so what we are going to do is we're going to talk about combining the strengths of declarative programming, probabilistic reasoning, and relational reinforcement learning. Hopefully this will be clear. And the point I want to make is there is a tight coupling between the transition diagrams that I talk about here. Each one of them flows from another one, right? So, and we'll talk about that, but it's described in better detail in papers that there is a formal relationship between them. We can make some claims and we can prove some things about the relationships between these transition diagrams. And what we are able to do thus is we are able to do both non-monotonic logical reasoning and probabilistic reasoning with incomplete domain descriptions, right? And that should hopefully be clear shortly. And in addition to that, we are able to do interactive and cumulative relational learning. What I mean is we use a mix of more classical machine learning like supervised learning, and we also use reinforcement learning, and I will get back to that when I talk about it. And all of this is implemented both on robots and has some simulation trials to help the learning as well. Okay, so let's go. So what do we have here? As an illustrative domain, I'm going to use this notion of a robot assistant who is going to walk around in sort of a map of the world that he has constructed, and the robot assistant has to move specific objects to specific people or to specific places. So the sorts of things that the robot can reason about are things like people, like places, robots, objects, and there are also specific instances of these, like you can have specific instance of the sort place, like office, library, workshop, kitchen, and so on and so forth. Okay, so this is there. So then let's get to the next one. That is the basic things that the robot can talk about, but here we are talking about the axioms, right? So the robot knows certain things about the world, how certain actions have certain effects, or what actions it can perform. But in addition to that, there are certain things that are unknown, because typically in any complex domain, you're going to have that you're going to not have all the information. So in this case, the robot may not know, for instance, that if it has an electromagnetic arm, it is unable to pick up a heavy object, or that a brittle object, if it tries to put it down, because of the way it puts it down, it's going to break, right? These are things the robot does not know, for instance. So the point here is that when it tries to reason with this incomplete knowledge, what is going to happen is it's going to have unexpected transitions, and or even if it achieves the desired goal, the plan that it executes might be suboptimal. So we want the robot to first be able to figure out something unintended is happening, and to then deal with it by sort of saying that I probably don't have the required knowledge. How do I go about learning that? So I talked about transition diagrams. How do we describe them? We want our reasoning to to the extent possible to be somewhat separate from the representation itself, as in we want to be able to use different reasoning schemes. So the actual description of the transition diagrams is done in an action language, and we use the action language ALD, which is an extension of action language AL. So action languages are formal models of parts of natural language that are used for describing transition diagrams. And here you can talk about basic sorts, like I talked about before, places, people, things. You can also have statics, fluents, which are domain attributes, some that change and some that don't change, and you have actions. And you have, in our case, 5 distinct type of statements that you can, in which you can use these basic vocabulary items, right? And we will see examples of this shortly. So let's go directly to that, and let's ask what does the logician's description of the world look like? Okay, so the logician's system description has a collection of statements in ALD which forms its system description, and this consists of a sorted signature, basic vocabulary items, and axioms which describe the dynamics using these vocabulary items. So statics could be things like the weight of the object, the type of the arm. Fluents could be things like the location of a thing, which is a place, or whether the robot has a particular object in hand. And similarly, you can have a variety of different actions. And now we use them to, of course, construct your axioms, right? And let us assume that the following are given to it in advance, right? Things of the form, say, causal laws, which say that robot moving to a particular place causes the location of the robot to become that place. Or let's take an executability condition, which basically the first one says that if the robot and the object are in different locations, hey, the robot cannot go about grasping the object. Right? Okay, so this is a very basic description. Now the thing to do then is to say I also have to talk about action capabilities, right? And to do that, we consider affordances or action capabilities as a combination of attributes of objects and agents, right, with reference to a particular action. So each action, we have a distributed representation. So each action can have one or more enabling or forbidding affordances. For instance, the first statement here, the way to read that is to say a particular action is impossible if there is a particular set of relations that forbid that action from taking place. And this ID is a variable that can be one of different ones. Like for instance, you can say this action is forbidden because there is a particular relation tied to ID1 or IDI here, and that has certain properties. So as a result of those properties of agent and the objects, this agent cannot perform this particular action. Similarly, you can also talk about actions being enabled. And oh, by the way, this NOT here is default negation, not typo. Okay, so the thing I wanted to highlight here is that it's a distributed representation, and this provides certain advantages. It will come later. Okay, so what does the logician have as input? The logician has a system description in this, so that we have seen so far, and a history of, say, prior actions and prior observations. The logician is given a goal, and we expect the logician to provide a plan to achieve the goal, and also give the next transition to be executed, right, in this plan. And this, of course, what I've described so far can be translated to many different formalisms. In our case, we translate it to answer set prologue. Why? Because answer set prologue has nice features like it supports non-monotonic logical reasoning. As a result of also encoding things like default negation, which means things don't have to be always true or false, they can just be unknown. So if you don't know something about some parts of the world, hey, you don't have to worry about it. You can reason about it when you know it, right? So, and all reasoning, that is planning, diagnostics, inference, is all sort of reduced to computing answer sets of this program that represent the beliefs of an agent associated with this program, right? So, okay, all good. The logician comes up with a plan and a transition. Not good enough in that, because we have to execute it and find a solution. So how do we get there? To do that, imagine, if you will, that you have a transition diagram. Someone gave you a magnifying glass, and you're now going to look at the same transition diagram at higher resolution. What's going to happen? You're going to probably discover new things, new objects, new relationships and stuff, but also certain things you can directly inherit. Like for instance, if you had, say, rooms like you have here, office, kitchen, and so on. Now, instead of having just rooms or places, you might have grid cells in those particular rooms, right? Like the C1, C2, C3, C4. But many of the rules you can just inherit directly. Right? And that is because moving between two places is not all that different, if you think about it, as moving between two cells in a particular room. Right? But another thing we have not done is we have not accounted for any of the non-determinism. We have not accounted for any of the uncertainty so far, and this is the place we do it. We get the fine resolution transition diagram and now say, hey, causal laws can be non-deterministic. Right? Actions can have unintended effects as well, and if we know them, what they could be, we model them, right? And we also introduce probabilities if we have that information, right? And these probabilities, just to make a point here, is that these are learned, right? So learning, planning, it's all happening together, right? But let us say we have come to that D subscript LR, which is your randomized, which is with your probabilities and fine resolution transition diagram. Now the other thing, of course, is that for any given abstract action I want to execute, let's say the robot wants to go from the office to the kitchen, it doesn't have to care about everything else in the world, right? So it doesn't have to reason about the whole world probabilistically at fine resolution, because that would be computationally too expensive. So what we also provide is for the robot to automatically zoom, and that is what this red rectangle is trying to show, to the part or subset of the space where it has to reason, right? And the nice thing, or what took a lot of time to do, is to establish formal relationships between these transition diagrams, such that any transition that you have in, say, the coarse resolution D sub H, you can sort of show that there will exist a transition once certain conditions are met in the sort of fine resolution transition diagram, and you can do this zooming and stuff automatically in a domain independent fashion. Right? And we have tried this for different domains, and you can show mathematically that there is this relationship between them which helps do this automated in a way. Okay, so this is done, and just as we had a coarse resolution and we translated that to ASP for reasoning, I now have a nice fine resolution description. What do I do with it? With the probabilities, in my case, I translate that to POMDPs. Right? I use POMDPs or hierarchical POMDPs, let it do my reasoning, and when it has some outcomes to report, that goes back to my Logician's history, and that it uses it for subsequent decision steps. So their sort of cycle is complete, so to speak. But hey, what about these question marks and exclamation points? There are going to be transitions because your knowledge is incomplete, which are not which are unexpected, right? And when this happens, the robot in our case interprets this as saying there is something about the world that I do not know. Maybe I should try to figure it out. And how do we figure it out? By learning, right? And that brings us to this component, which is the relational reinforcement learning part. And what are we trying to do here? Remember, we are trying to deal with unexpected state transitions which trigger interactive learning. And here I'm borrowing some terminology with permission from John Laird from University of Michigan. So learning he tries to talk about as being sort of in two classes, like things which are procedural, which happen all the time, and which are many times even involuntary, right? And the other one is more knowledge based, that is triggered to explicitly acquire some action, some knowledge, or something that is learning that happens as a result of you acquiring some knowledge, right? And the point I want to make here is we are actually doing both. So there is some learning that is happening along the way all the time, and there is also learning happening which is explicitly triggered in demand for when you have a demand for acquiring some new knowledge, right? And in our case, what do we want to do? We want to identify state action combinations that result to these transitions that we are unable to explain. And we formulate this here again, like I said, you could try other things. You could even try supervised learning if you have the data. In our case, we do reinforcement learning formalism and do part of this in simulation and part of this in real robot trials, but we don't do reinforcement learning in the whole fine resolution transition diagram. Again, that would just be, well, computationally expensive and also silly. So instead, what we do is we exploit the relational representation that is encoded in our transition diagrams, and in addition, we use the ASP-based reasoning or inference to establish relevance. We are basically saying that when you are trying to do a particular transition and something goes wrong, you do know, based on how you have taken the effort to construct the transition diagrams, that only a certain subset of your transition diagram is relevant, and you also know what those things are, what fluents are relevant, what static properties are relevant, and you only do your MDP over that subset of your state space. Now, again, we have to learn this relational representation. We want to generalize, right? And in order to generalize, what we do is we start constructing a binary decision tree. And again, details are in the paper, but essentially, if you take a path from the root to the leaf, you are trying to have partial state action descriptions. And what it allows us to do is cumulatively acquire experience and go from, say, specific knowledge to more generic versions of those. And I will talk about that in just a second when I show an example. And at the same time, this is not just you construct the BDT and use it later. As you're constructing it, you're using the experiences you've acquired in the subsequent episodes to help do your learning better. Okay, but there is one other point that comes up now is in order to do this generalization, it is not just that single particular transition you have to look at. You should also be able to look at related transitions. And the example I have here is like a blocks world. Let us assume you are trying to stack blocks of different colors, shapes, and sizes. I try to put a blue cube on the red prism, does not happen. I try to put a red prism, or cylinder on a blue prism, it still does not happen, right? Now the problem here is not that the color is red or whether it's a cube or a cylinder. The problem here is that you're trying to put stuff on a prism which is never going to happen. A pointy end, it's going to fall out, right? So what we do therefore is we use this ASP-based inference to not only to do figure out what is relevant, but also say what properties should I explore further, right? Maybe I should explore this color and shape and size further in order to figure out a more generic version of this, in this case, the axiom that nothing should be placed on a pyramid, right? Or a prism, right? So in that case, what we do is we use the choice of different MDPs are constructed by ASP-based reference. You explore it, and the binary decision tree now captures your experiences across these different Markov decision processes. And when you have to construct the axiom, you can again parse the tree from the root to the leaf in different ways for different axioms you want to find. And when you extract these paths, you might get some specific instances or more general instances. So we have some additional filters so that over experiences, as you acquire more experiences, you get better. For instance, if you got on the previous slide that a blue cylinder should not go on a red prism, and later you got a more generic version that nothing should go on a prism, then you will keep the more specific ones and general ones and eliminate the specific ones. And in addition, we also use this knowledge on the robot to actually try it out. And if it does a good job, of course, you know that this is a valid axiom, right? And the good thing, of course, is because it's non-monotonic logical reasoning, if you make a mistake, you can still recover. Okay, so I'm just going to show one sort of execution trace, and then I'm done, right? So the execution trace is going to take the following form, which is basically saying that let's say the goal is to have at the end of your plan that some cup should be in the office, right? So when you're done, a location of some cup C, whatever cup that might be, should be the office, and it should not be in the robot's hand, right? And the initial knowledge you have, a subset of it, is that the robot is in the office and the surface of the cup is brittle, right? Let's say we have this. And what you do is the robot says, oh, I don't know where exactly there is a cup, but I know that cups are usually in the kitchen, and I know I have 3 cups somewhere. So therefore, the location of the cup is in the kitchen. So the plan is for the robot to move to the kitchen, grasp it, and bring it back to the office and put it down, right? And let us assume the robot manages to go to the kitchen. It still has to grasp it, and grasping requires it to know where it is. So it does some additional perception. So I'm showing logical statements here, but each such logic statement or action is executed probabilistically. Robot moves to different cells, searches for it. It sometimes doesn't find it. Then it finds it reliably, and then it grasps it and brings it back to the office, successfully puts it down there somewhere on the table, and now it's like, yes, I did it. But then it opens its eye and says, oh, sir, what's going on here? The cup is broken, right? So then what it does is can over some simulated trials, in this case you want to do simulated, you don't want to keep breaking cups, but you can also do a combination of simulated and real trials, and then figure out that if the robot puts an object down and the object is brittle, then the object is going to be damaged, right? Just as an example. Okay, I'm not going to go over this, it's there in the paper, that we are able to show that we are able to discover different types of knowledge, that we are able to use the directed exploration to significantly make it much more efficient and also automated, and at the same time reliably accurate as you get more and more experiences. It has some robustness to noise, and any errors are primarily you get the specific version instead of the more generic version of the axiom. And the key thing for learning and planning putting together, it does improve plan quality. So I'm just going to focus on one thing. So if you go, say, for the executability condition, initially you don't know that under certain conditions certain actions should not happen, and so you generate more plans, but with the axioms you generate fewer plans, and as you get more and more knowledge, all of these axioms plans are actually accurate, right? So that basically brings me to the conclusion that we are able to represent and reason with different descriptions of knowledge and uncertainty, and this is primarily aided by the precise relationship that we are able to define between the transition diagrams and to do interactive discovery or learning of the domain axioms. And we want to do more active exploration, and I have here names of both colleagues and students and also the funding sponsors who have supported this work or continue to support this work. So, and if people are interested, there is a whole sequence of papers, but everybody has them, so I'll stop here.
Thank you. So I guess that many people here would like to use heuristics on top of your planner. Mm-hmm. So do you think about using some kind of PDDL compilation from your language so that you can deal with
so for the so I was primarily interested here to try and do the combination between the transition diagrams, right? But if you wanted to use a PDDL like thing instead of using an ASP based thing, should be fine, should not be a problem. Right? Just that ASP is a lot more powerful in terms of the kind of reasoning we want to do. And if you wanted to, you can include heuristics. I just didn't do it so far.
Okay, thank you.
Thanks.